this section, we will be discussing the aspect of matter waves with respect to interference patterns. In terms of the possibility of waves interacting with one another, you can have a situation that's sometimes referred to as interference. There are two possible types of interference that we will consider. The first is constructive interference. This is when the crests of two waves happen to coincide with one another and results in a new wave that actually has an increase in the amplitude. For example, if I have two waves as shown on the right here, the top wave might be a wave that is sinusoidal in shape. It may be moving in the direction of left to right. You'll notice that then if we had a second wave underneath it that say is moving from right to left, and that if at some moment in time the crests of these two waves simultaneously correspond to one another, we then get in a new wave, which is shown down here at the bottom, where the amplitude of the resulting wave has essentially doubled. Therefore, you can sort of line up the crests of the two individual waves, which both have amplitudes of 1 on the y-axis, and see that the sum of those two things would be a new wave with an amplitude of 2. You'll notice that the nodes, the place in each of the individual waves where there is no amplitude, results in no amplitude for the summation, and that is shown by the second dashed line here. Likewise, the troughs will become deeper as a result of this constructive interference. Alternatively, destructive interference is when the waves interact such that the wave amplitudes will cancel one another to some extent. And so shown here, we have two waves, one moving to the right, the top wave, and one moving to the left. But in this case, they are out of phase with one another, such that the top wave has a crest at the same moment in time when the bottom wave has a trough. And this results in a canceling of the amplitude such that the sum of those two waves actually has no amplitude at all. Once the waves have passed each other, then you end up having the individual waves having exactly the same properties as what you started with. A more complicated situation can occur if the two waves involved have different frequencies, or possibly have the same frequency but are somewhat out of phase with one another. Then you have a situation where, say, for example, the top wave is moving from left to right and has a higher frequency than the bottom wave, which is moving from right to left. In this case, where we have constructive interferences when both waves are positive amplitude or negative amplitude, and then in some situations, one of the waves will be a positive amplitude, but at that same moment in time, the other wave will be negative amplitude. The resulting wave will have a very complicated wave nature, as shown at the bottom here. As an example shown here, we have two waves that are moving in opposite directions. The wave that is in green is moving from left to right and has the same frequency and wavelength as the blue wave that is moving from right to left. The red represents the sum of those two waves as they interact with one another over the period of time associated with this standing wave. Shown here is a source of light that will produce electromagnetic radiation having wave properties, and the waves that are being emitted are shown here as wave fronts. These are essentially lines representing the crests of the wave as they travel from left to right. The curved path is a result of the light source being a circular light bulb or something. If you have these wavefronts interact with a barrier of some sort that happens to have an opening, the waves will pass through the opening, but then will generate new wavefronts on the other side, which are also curved, and it will act as if it's a new light source. These waves can then interact with some sort of detector or possibly a screen to be observed. Alternatively, the behavior that particles would have, say very small particles such as electrons, focused on a barrier with a single slit in it, would be, you would expect that when the particles strike the barrier, they would either be absorbed or possibly reflected by the barrier, but the particles that pass through the opening should pass straight on through and then strike the detector, producing only a single spot on the screen. The crucial thing about the light is that the diffraction pattern for the wave has to be a result of the wave having a wavelength similar to the size of the opening. For the particle, the opening has to be big enough to allow the particle to pass through. Shown here is a diagram representing the classic double slit experiment. In this case, we have a light source which is producing the electromagnetic radiation having wave properties. The lines are representing the crests of the waves that are then focused on a barrier having two openings. As the light passes through the openings, it will produce a series of curved lines from the diffraction as it passes through the opening. In the case of the top slit, this would produce the curved lines that you see here in blue, whereas the bottom lines are shown in red. Note that you have the intersection of these wave fronts in certain places, and that this would correspond to where two crests are coming together and producing constructive interference. Alternatively, there will be situations where a crest and a trough will interact, and that will produce destructive interference. The pattern associated with following where the crests are interacting will produce bright spots on the screen, and the interactions of the crests and the troughs will produce no light at all, and this is due to the destructive interference. Shown here is an animation that represents the double slit experiment and the resulting interference pattern. Note that you have the series of bright spots and no spots that occur over on the right hand side where the screen would be. The behavior of a particle source interacting with a barrier that then allows the particles to pass through because there are two openings. You might expect there to be just two places on the screen that would produce any kind of response to the particles that have passed through. This is indeed what is observed for relatively large particles, and so, for example, if we have a source of alpha particles focused on a double slit, you see just two lines on the screen that match up fairly well with where the particles are passing through the two openings. However, if the particles are smaller, say for example electrons, the electrons tend to start to have some wave properties. So, according to the DeBroglie equation, there's an inverse relationship between the wavelength and the mass of the particle. So, if the particle is a very small mass, we would expect the wavelength to be bigger. And as a result, this wave property of the particle might more closely match the size of the slit, and you end up with a situation where you start to see multiple bright spots on the screen as a response to electrons being diffracted through those openings and having the characteristic interference pattern that would be characteristic of a wave. We can derive the DeBroglie equation from two important relationships that you should be familiar with. The first is Einstein's famous E equals mc squared, which states that the energy of matter can be related to the mass times the speed of light squared. And then also Einstein came up with the important relationship of the energy of a photon and its relationship to frequency. In this case, energy is equal to Planck's constant times the frequency. In addition, if we substitute the frequency for the relationship of frequency and the speed of light, which basically is c equals lambda times nu, and rearrange and insert into this equation, we could come up with a further relationship that relates the Planck's constant times the speed of light divided by the wavelength of the photon. Taking these two equations and setting them equal to one another, we can come up with a new equation which says that the mass times the speed of light squared is equal to Planck's constant times the speed of light divided by the wavelength. You'll notice that c appears on both sides of this equation, so we can cancel out one of the c's on both sides, and for a particular particle having some mass, typically it is not moving at the speed of light but something slower, so we would replace the symbol c with a v to represent the velocity, and that gives us the DeBroglie relationship, which states that the wavelength of a particle wave of matter is equal to Planck's constant divided by the mass of that particular particle divided by the velocity of that particle. Notice that the denominator of this equation is essentially the momentum